So why do you still use processes? So if threads are cheap, mainly for the purpose of reliability, and also because you can easily kill a thread and reclaim its resources because it's all isolated, while it's very hard to just simply kill a thread and completely reclaim all the resources, because it could be possibly sharing stuff with other threads in the same process, and it makes things expensive. So let's consider a web server. So a web server is a great example of a place where you use processes. The widely used Apache web server uses a process-based model. So you get a network message from a client. So let's look at what happens in a web server and reason about why processes are useful. So you get a network message from the client. You create a child process and you send the URL. Okay, so this is the URL that the client wants. You fork off a process which actually does the real work. So it fetches the URL data from the disk, it composes the response, sends back the response. So let's say that the server has a configuration file open for writing, right? So it's doing some bookkeeping, it's maintaining a whole bunch of other state. A web server does more than just fetch URLs and stuff, and that's one of its primary tasks, but there are other things that it also does. Like, for example, making sure that it's still up and running and making sure that it recovers from errors in the I/O system itself and retrying them, managing the TCP IP links. And so let's say that the server itself is actually has a configuration file for writing. And let's say that you have a small bug in the program where fetching the URL from the disk causes things to overflow, and it may overwrite the file. Right? So essentially, we want to prevent the child from overwriting the configuration, because if you fetched bad data and served it back, then you possibly just screw up one request, right? But if you overwrote the file, then the whole web server goes down. So essentially, in some ways, it's separating out the critical from the non-critical components. The TCP/IP and all that runs within a single process, and that process has nothing to do with the child process that actually fetches the URL and could possibly get corrupted. So how does the server know the child serviced the request? So essentially, how does it know that the child has finished in case it has to retry, right? So in this case, it needs a return code from the child process. So when the child process exits, it gets back to the server with a specific return value. So this is one important difference. When the parent exits, then it does not need to inform anyone. But when the child exits, it has to inform the parent that it's finished. So, so one of the things, so I had just recently spoken about fork, and fork essentially creates a new process. So a process forks off another process. So a process creates another process. Okay. There's also another thing called exec. So exec is an ingenious idea, and we'll look at why it's useful in a second. Okay. But essentially, let's say that you want to create a process with a file name, and you want to close the file in the child itself. So you have and also you want to change the child's environment, right? So let's say that in this case I have a create process file name. I want to close the file in child, so I've created a process with the file name and a specific list of a specific list of children, and essentially what you need to do in this case is that every single time you'd have to call the create process with the file name, the file descriptor itself, and the new environment. Okay, so what fork does is essentially splits the process into two, and if it returns 0 on the child, or it returns the PID of the child and the parent, so that you know what exactly. So if you look at the code itself, you'll understand. So you forked it off, and then since the child is duplicated at that point, from that point on, the rest of the code is common between the parent and the child. But you want the child to do something slightly different. So essentially, you have to have an ugly if-else component where you say if blah, if parent, then wait for the child to return. And when the child returns, finish up. And if child, then close the file and return. Okay, so essentially it takes slightly different code paths. And really there is no business. The parent has no work beyond this point. The only reason the parent exists is to wait for the child to finish closing the file. So what exec does is essentially overlay the parent with the child. So you don't have to have this code sequence where if you're a parent, then all you're doing is just waiting for your child, right? You don't need that. If you're a parent and you do an exec, essentially you do the work that you need for the child in it, but you've just taken the child and overwritten the parent process. So decoupling fork and exec essentially lets you do different things in the child's process environment without adding to the create process API. So without adding stuff into the fork process, right? You don't need to pass things into it. So essentially, so in this case, for example, if int PID equals get PID, fork, if get PID not equals PPID, that is you're the child, then child continues there, do different things. And when fork creates a child process that inherits identical copy of parent variables in memory, identical copy of all parent CPU registers, except one. And that one is the program counter because the child is executing the next instruction after the fork, not exactly at the fork. At the time of the fork, the PC is on the fork call itself. So the parent and child execute at the same point after the fork returns. By convention, for the child, fork returns 0. By convention, for the parent, fork returns the process ID of the child. And then fork returns some of the code itself as a convenience, but you could always just use getPID to identify the process. The exec process allows the process to load a different program and start executing at main. So it essentially overlays the parent with the child. Okay. It allows the process to specify also arguments and similar to your fork call, and in order to specify what you want to start up. And if the call is successful, then the current process is dead and the one that's new has started to run exactly at the point at which this one finished. But it could possibly run a different program, right? In fact, it's not run. So what fork does is essentially create a duplicate of the parent, and then from that point onwards, it could possibly execute something else, but that something else also needs to be part of the fork call or part of the same program. So if you wanted to call fork and then run foo, then foo has to be defined and declared within the program itself. But with exec, essentially that foo need not be. Foo can be a whole different separate program that exists in your system, and when exec calls it, foo gets called in and then overwrites the current process. The code, the stack, and the heap are all overwritten. The text page comes from wherever the foo resides. All right. So here's a question that you want to ask yourself. Which call creates a process? Fork, exec, or both? Right. So if you can answer this question, then I have confidence that you would have understood some of these mechanisms. I'll look at a specific example in the next slide that will clarify things better. All right. So what we're going to do is look at the difference between fork and exec with an example. So in this case, I have a parent process, a main. I essentially remember the parent process ID. This I need in order to distinguish between the parent and the child following this fork call. Following this fork call, I do a get PID. I check it against the parent ID. If it's not the parent ID, then it's the child that's running. I then do an exec and then start running this program called calc. Okay. Else, I'm essentially in the parent, and then the parent starts to continue here, and I start waiting for the child. So at this point, I'm waiting for the child to finish and come back with a return code. Okay, that is done. Okay, so what happens at this point? An example of this could be a shell forking of a specific program. And I wanted to pay careful attention to this because this is part of your first assignment. So int PID equals fork, so you do a fork call at that point. If PID equals 0, then you want to close the history and exec calc so you're in your child, else you're going to wait for your PID. Okay, and I'm going to the top part over this line. This is all user, and the bottom one is all OS. So this is the data structure in the OS. This is what the user program looks like. Okay, so in the process control block itself, we're still in the parent. Now there's only one process. Let's say that the parent has a PID of 127. You have some open files associated with it, and maybe the last CPU that you ran on. Okay, so the next thing that's going to happen is when you do a fork, is a duplicate is going to get created, right? So in this part, you had what happened was this is now the child, right? And there's a separate process for the child itself. Okay, once the child is created, you see there's a new PID. The open files have all been duplicated, and all the control state as well. Then what's going to happen is when the exec is called, the child is going to get overwritten with the calc program, and you can see immediately the open files part has cleaned up. So there is no open files anymore. Previous to that, there was a dot history which was copied in from PID 127, which was a parent. And now when there's an exec, the calc program starts running, all the open files have been closed, and the new program that's running is really calc. Okay. When that happens, now you've replaced the child process with the calc main. So you've got a whole different program now running at this point. If you had a fork, then with purely a fork, this would not have been possible. Essentially, this calc main would have had to be defined within this program. So calc main would have had to reside in that. But now calc main can reside in any part of the system, and we can transparently fork from the parent and then exec this. So here's another view of this, looking at the stack and the heap. So in this case, your main AS2, we've got some heap allocation, we've got the actual code. When this happens, you create a whole new stack and a heap, and all of that happens. And then you've overwrite, when you have the exec or the calc call, you overwrite the dot history that shows a new thing has happened. And then what's going to happen is that you overwrite the stack and the heap and the code with the whole new separate program. So when fork happens, you essentially duplicated the stack, heap, and the code. When exec happens, you've overwritten it. You've got a whole new stack, a whole new heap, and the code comes from whatever program that you specified in the exec parameter. So the immediate question is, obviously exec is more powerful in some ways because it allows you to run arbitrary programs when these arbitrary programs don't even need to be part of the whole parent process. So the simple implementation of fork essentially allocates memory for the child process, copies parent memory and CPU registers to the child. So it creates a duplicate, right? This is the expensive part. If most of the time, what we do is essentially we call exec after calling fork. That is, we create a new process, and then the goal of this new process is to essentially run a whole separate program. Then what you see is that the state has been clobbered, right? When you forked, you copied a whole bunch of variables and all of that into the child process. And for what? All you did was call a separate program that overwrote everything. All the stack, heap, code, everything was clobbered, right? And this whole new clean slate appeared. And the child process is also likely to close all the open files in connection. So most of the time, if all we're doing is forking off children whose sole purpose is to run a new program, then the memory that was copied during the fork itself is useless, right? So we don't need it. We really overrode it. So Linux or Unix systems also provide this another version of fork called as a vfork. A vfork is a system that creates a process without creating an identical memory image. So you create a whole new separate clean process, and the child, all that it does is it only it has no state associated with none of the global variables, none of the stack. All it does is the only thing, in order to do anything useful, it has to all call exec immediately. If it tries to do anything else, it's all just going to be cut up because there's no other state that's part of the child. Everything is a clean slate. So you start out with a zero in all the pages on the stack and the heap. Um, and if you have copy on write, um, to implement fork, then this avoids the need for the vfork, because when you copy, you're not really copying. You're just giving the illusion of copying. So logically, you've created the operation of copying, but nothing is copied unless you manipulate the pages. And so unless you start modifying variables. And we look at this more in detail when we study virtual address spaces. But if you have copy and write, then vfork is not that much more efficient than fork. Or in other words, I should say that fork is pretty efficient. So the final system call we want to deal with is exit. This is called after the program finishes execution. It takes the result of the program as an argument, closes all the open files and connections, deallocates the memory, deallocates these OS data structures that correspond to the process. It takes the process out of the ready queue in the end. And it also checks if the parent is alive, because if so, it holds a return value until the parent requests it, right? So in this case, it really returns a zombie until the parent does a wait PID and gets back the call. If not, it just deallocates all the data structures and the process is dead. So if the parent is alive, then it needs to return a value, and it needs to maintain this value somewhere, and so it maintains it in a zombie state while the rest of the stuff is cleaned up. So for example, memory and all of that's gone, but at least the return value does need to be held. If not, if the parent's not alive, then it just deallocates all the data structure and the process is dead. And ultimately, you clean up all the waiting zombies as well when you return back to the process. Essentially, this is a form of garbage collection. An important system call that the parent uses to signal to the child that is waiting for it is what's known as a wait. A child programmer this returns the value to the parent, so the parent must actually arrange to receive the value somewhere, right? So it needs to specify that it needs the value to be copied somewhere. So the wait system call serves this process, or serves this purpose. It puts the parent to sleep, waiting for the child's result. And when the child calls exit, the OS basically unblocks the parent starts running again. And whatever value that the child passed into the exit appears as the return value on the wait call in the parent. And if there are no children alive, then wait returns immediately. So there are no children to wait for. And also, if there are zombies waiting for the parent, then wait returns one of the values immediately and deallocates the zombie itself. So it deallocates children as well, if there are any zombies that are associated with the parent. So tying it all together, as part of the first assignment, we asked you to implement a UNIX shell. Essentially, a UNIX shell would be you wait until you have an end of file or an end of file character returned on the shell. So this essentially terminates the shell itself. Shell is just a process, just another process, right? So you read the input that's provided to you on the terminal. You handle regular expressions, whatever special calls that the shell is expected to handle, and then you fork. Anytime you want to start running a new program, the shell itself is running separately, and you fork. And then the fork call essentially, if the PID is 0, which means it's a child, starts executing the program. And one of the different things is you're going to get signals that need to be handled. So we'll look at in more detail into signals in a couple of weeks. But essentially, you have these different operations or events that the OS tells the process about, right? So for example, someone hits a special keystroke, Control C, the OS passes on this information to the process saying it's a SIG kill. So someone's trying to kill you. If you need to do any cleanup, please do so. For example, close a file. Control Z is SIG stop. Essentially, this is one where the process is suspended and not to start over again. And this is also something that's passed in. There are quite a few other forms of signals that the OS passes out. And it also the shell itself needs to support things like pipes, input-output redirection, and this it would do by essentially having multiple execs. So you have one exec, and then you have another one, and then you chain these, right? So you pass the output from one into the input of the other, and so on and so forth.